Hello all, welcome to the course AI driven perception, learning and mapping for drones. This is the lecture 6 which is going into a deeper dive in multi-layer perceptron. The learning objectives of this lecture are focused mainly on the training parameters, which is while training a single or multi-layer perceptron, what are the factors that affect the learning algorithm. So in this lecture we will focus mainly on the factors affecting convergence, the influence of activation functions when we are trying to develop the learning algorithm for continuous weight updates. We will also take a deeper dive into the properties of backpropagation, the effects of learning rate, and how momentum could be introduced to solve some of the issues related to learning rate. Finally, we will also take a deeper look into types of learning, which is sequential or batch learning, early stopping, and we will also focus on a curve fitting example and see how generalization is affected, what it means by overfitting or underfitting, and why model complexity is very important. And finally concluding the lecture with focusing on the regularization and its effect in curve fitting. Okay, so before we start, let's do a quick recap on a single layer neuron. So as we can see here, we have the single layer neuron on the right. So we have inputs which is x1 and x2, corresponding to that we have its weights, and hence the output, which is denoted as z here, can be written as wx plus b, where b is the bias term. So the x0 and w0 relate to the bias term. Finally, we can write the output y as f times z. In this particular example, let's keep the activation function as a linear function, which is why y is equals to wx plus b. Now using the chain rule, relating it to the loss, we can write dou L by dou w is equals to dou L by dou y times dou y by dou z times xi. Now we can also define the error which we get while passing the input with corresponding ground truth d. So error E can be written as 1 by 2 d minus y whole square. Now as we can observe in this particular equation, the gradients primarily depend upon the activation function, or rather the derivative of the activation function, and the input which is passed to the neuron. Okay. Now let's go over the effects of the activation function. So let's take sigmoid activation as an example. Sigmoid activation is defined as y is equals to 1 upon 1 plus exponential of minus x. So in this particular graph that we see, the blue curve is actually the sigmoid activation function, and we can see that its range goes from 0 to 1. Now the curve on the red actually highlights the derivative of this activation function, right? Now observing the curve, we can observe certain disadvantages in sigmoid activation function. First is that the range, although it is 0 to 1, it is not zero centered, in the sense that its center lies around 0.5. Now although it is not zero center, it does result in better optimization, since the weights can update in both positive and negative direction, because we observe that the gradients could exist, like the derivative exists in the plus and minus of the x axis. Now although it has better optimization, it does not have very strong gradients, because we can see that the derivative curve only lies from 0 to 0.2. Right. So throughout the curve, the magnitude of the derivative of gradients is actually not very high. So if we look at the equation again, which is dou L by dou w is dou L by dou y by dou z times xi. This dou y by dou z is essentially the red curve which is highlighted here. Now there is a phenomenon that is observed, which we would again discuss in detail in the subsequent lectures, which is known as the vanishing gradient problem. So we have seen that the update to the weights is given as w is equals to w plus delta w, and this delta w relates to dou L by dou W. Now essentially if the magnitude of the derivative of the activation function, which is dou Y by dou Z, if this value is very small, which we can observe from here that it is actually very small, right, then the overall delta W would be very small, and hence there would not be a meaningful update in the weights during the learning algorithm. Okay. Now let us look at tan H activation function. Tan hyperbolic x is written as the equation given below, which is e exponential to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. In this curve we can observe that the green color is actually the tan H activation function, and the yellow curve that we see here is the derivative of this particular activation function, right. Now there are certain advantages of tan H compared to the previous activation function, that it is zero centered. Essentially its midpoint lies around the origin, and similar to sigmoid activation function, it has better optimization because the gradient could be in both the positive and negative directions. Now again, compared to the sigmoid activation function, there is a stronger gradient observed in the derivative curve. So if I see the yellow curve, we can see that its magnitude is essentially pretty high, right. It is not contained into a smaller number, right. So hence the gradients would result in a meaningful update rather than getting a very small magnitude. However, in this particular graph also we observe that once mod x is very large, which is essentially these parts of the curve, in these particular parts the gradient value is very small. Since the gradient value is very small, we can observe that this value would actually again be very small for mod x greater than 0, right. So even tan H activation function could result into vanishing gradient problems when the value of x is either very high or very low, which is either an extreme of positive on the positive axis or an extreme on the negative axis. Okay. Now we discussed about the learning algorithm last time, which was on the weight initialization parts. So comparing that to the single layer neuron we saw earlier, theta, which represents all the learnable parameters in the single layer neuron, W1, W2 are the learnable parameters. The goal of any learning algorithm is to give us this particular optimization, which is arg minimum of E theta, and we should get an optimal theta star here, right. Now we also saw this last time, that essentially for any learning algorithm we can start at a random initialization setting which would correspond to a point A, let us assume, and then throughout the learning algorithm we would essentially reach a minima value which would again correspond to say a different point B, right. So now if we relate it to dou L by dou W, which we saw in the previous lecture, previous slides, we can write this equation. Now what we want to observe in this particular graph is to project the value on the weight axis. So we are looking from the z axis and looking at the axis which is W1, W2. Okay. Now before we go into that analysis, let us just take a very quick example. So let us take a example based on the single layer neuron itself. Let us take the input as x1, x2, which is given as 1, 2. The weights are given as 0.5, 0.5 and W0 is 0. So essentially in this particular example our bias becomes 0. Now the learning rate is given as 0.1 and we assume an activation function which is linear, and hence the derivative of the activation function, which is dou y by dou z, is given as 1. The corresponding ground truth for this particular input D is given as 0. Okay. Now again, as we saw earlier or as we performed even in the earlier examples, we'll first compute the forward pass. Once we compute the forward pass, we'll calculate the error and we'll calculate delta W. And once we calculate delta W, we will upgrade the weight. So W is equals to W plus or minus delta W. So the forward pass Z is given as W times X plus B. Since B is 0, we get Z as 1.5. Now since it's a linear activation function, the output of my single layer neuron is 1.5. Finally, if we compute the error E, which is given as 1.2 d minus y whole square, the error is 1.125. Now what we would do is we would calculate the gradients necessary for the weight update. So dou L by dou y is given as minus d minus y, which is minus of 0 minus 1.5, which is 1.5. Since we have a linear activation function, dou y by dou z is 1. So the scalar product, which is dou L by dou y times dou y by dou z, is given as 1.5. Since we have calculated this part of the gradient update, let's now perform the gradient update, which is essentially delta W. So dou L by dou W1 is given as 1.5 times the input x1, which results in 1.5. Dou L by dou W2, which is 1.5 times the input, results in a value of 3. Finally, since we calculate the gradients, let's calculate the gradient update, which is given as this. Sorry, it's given as minus. So W1 can be written as 0.5 minus of the learning rate, which is 0.1, times the delta W. So W1 after the weight update is given as 0.35, W2 after the weight update is given as 0.2. Now since we have the weight updates, let's look at a interesting phenomenon that could occur while training the particular single layer neuron. The weight update from 0.5, 0.5, after the weight update we get 0.35 and 0.2. Now let's look at this equation again. So dou L by dou W is dou L by dou y times dou y by dou z times the input. Now we observed in the derivative of activation function that generally this term, which is dou L by dou z, is a positive, it can be a positive number. And now let's assume this whole first term is a positive number, which is dou L by dou y times dou y by dou z. In that scenario, dou L by dou Wy is directly influenced by the input. Now this curve that we see here, which is W1 W2 curve, which is something we saw from the error surface, if this phenomenon exists that dou L by dou Wy always depends on the input, then the gradient update would either be in this range, which is the first quadrant, or it could be in the third quadrant. If that is the case, then let's assume that this is my hypothetical optimal, which is W, which is highlighted by this particular dot, which is highlighted essentially by theta star. The gradient update would always follow a zigzag pattern, which would either be a horizontal line or a vertical line, and so on. So essentially, instead of following the blue line, which would lead directly to the hypothetical optimal theta star or W1 W2, we would actually have updates which are in a zigzag manner, and this actually affects the convergence. So an example, if we elaborate it more, let's assume that after the gradient update the values are 0.35 and 0.2. Now let's assume that the optimal is given by this particular number, which is W1 is 0.8 and W2 is 0.1. In this particular scenario, if I started from 0.5, which is W0, and the update then was 0.35, 0.20, which is W1, and I essentially want to move towards the optimal, in this particular setting W1 should actually go up and W2 should go down, and this should happen simultaneously, right? Because I want to move to an optimal. However, due to this particular phenomenon that we just discussed, the gradient update would always be either in plus plus or minus minus direction, and hence the gradient update would actually always be in a zigzag manner as we see in this graph. So the optimizer would never take the blue curve that is highlighted in the figure, it would always try to bounce back and follow a zigzag figure, right. So this is one thing which would affect the convergence. Since I do not directly optimize and get theta star, I reach it via a zigzag path. Okay. So again, when we are doing training with any particular learning algorithm, the gradients can actually focus, the gradient update would actually focus on this particular equation, which is dou L by dou Wi. The gradients actually depend on the derivative of the activation function and the particular input, right. And as we saw in the last example, the sign of the gradient now depends upon the input. If that happens, then we observe a zigzag path to theta star rather than an optimal straight path, right, and this affects the convergence. This affects into inefficient learning, and this affects into a slower convergence throughout the whole training procedure. Okay. Now let us take a look again at the backpropagation that we discussed last time. So backpropagation essentially provides an approximation to the trajectory in the weight space computed by the method of steepest descent, right. Now there are certain properties of backpropagation. For example, the gradient descent over all the network weight vectors. So it is not particular to W1, W2 or any particular part of the hidden layer. The same algorithm is used to update the whole set of learnable parameters. And the second part is it is easily generalized to arbitrary network architectures. In particular, in this in the last examples that we saw, we took a single layer perceptron. We also followed chain rule using for multi-layer perceptron, and throughout, although we had a complicated way of the chain rule, the backpropagation algorithm essentially remains the same. Now the goal of the algorithm is to find a minimum, and in general it could be a local or a global minimum. However, in practice it often works very well. Our goal is to minimize the error which we defined in this lecture and have been defining in previous lectures, which is E of theta. Essentially we want to use backpropagation and reach an optimal value, which is theta star. And once we attain theta star, we would use this theta star for inference, and hence inference is much faster because I already have an optimal set of parameters. Okay. Now let us look at the effects of the learning rate. So we know that the weight update rule is given as W, which is W minus eta of dou E by dou Y. So again we are using the error dou L and dou E a little bit interchangeably. So please do not get confused. Now if we look at the graph on the bottom left, we can see that there is a curve of error which we denote as E here, and on the x axis we have different weights, right. So this is a simplification of the error surface we saw earlier, which is just focusing on W, which could be W1 or W2, right. Now we can see that this is the optimization algorithm which we even discussed in detail last time, which is we find a random initial value, and from the random initial value, using the steepest or the gradient descent algorithm, we move towards the W, which is the minimum, right. So we move in this direction to attain W, and essentially W could be theta star. So this is the minimum value where we want to achieve. Now the learning rate's influence is essentially on the step size. So this jump depends on the learning rate. Now if we relate the left figure to the right figure, we can see that so the right figure actually shows the optimization using different learning rates. So we can observe that the red curve is essentially when the learning rate is very high, which is essentially this curve where the learning rate is very high, in this particular curve, we observe that there is an oscillatory motion, right, when learning rate is very high. When the learning rate is very low, which is essentially the orange line, we can see that it follows a very slow convergence, right. And again, we also have the blue curve which highlights a good learning parameter, which is essentially the blue curve eta, which is the good one, right. And we can relate the effects which are observed in the right graph from the left graph itself. So if I decrease my learning rate eta by a very small margin, I would observe the convergence to be very slow, right. And similarly, if I increase eta by a very large margin, it would essentially start oscillating. So if I have a high learning rate, we observe a faster initial progress, which we observe even in this particular curve, where the red actually progresses very quickly to a low error. However, it actually will overshoot and start oscillating, which we observe in the red curve. A low learning rate, which is essentially the orange curve, is more stable, but it is very slow during the training process, and we can observe this, that the convergence is very slow, the rate of decrease in error is very slow. And lastly, we have a moderate learning rate, which is essentially a good balance of speed and stability. So essentially, we want to converge quickly, more reliable convergence to a good minimum, which is observed in the blue color curve. Okay. Now, while training the model using any particular learning algorithm, focusing more on the eta, which is the learning rate, there are certain heuristics that we could follow. For example, there could be separate learning rate for each learning parameters. In our example, we had W1 and W2. So each of them could actually have separate, which is eta 1 and eta 2, separate learning rates. Second is, each learning rate is allowed to adjust after each iteration. So after each delta W, we can actually keep updating the learning rates. Okay. Now again, there are two more heuristics that are generally used, which work well in practice. So if the derivative of the cost function has the same sign over several iterations, we can increase the learning rate, and this is something you can relate it to the zigzag curve. If the derivative of the cost function alternates the sign over a lot of iterations, we can decrease the learning rate. So these are 2 points, which is point 1 and point 2, which work well in practice. Okay. Now during backpropagation algorithm, as we observed in the plots before, the influence of learning rate, a smaller learning rate would actually have smaller changes to the synaptic weights, where we observe a smoother trajectory. However, it is very slow towards convergence. Now if we have learning rate which is very high, we observe a drastic update in the synaptic weights. However, it has an oscillatory behavior, right? And a simple method to tune the learning rate throughout training the whole model or using any learning algorithm is using the momentum term. So let's assume that the gradient update after nth iteration is given by this equation. So W at nth iteration is Wn plus delta Wn. Now let's try to integrate the momentum term here. So after integrating the momentum term, W at nth iteration is Wn plus delta Wn plus alpha times delta W at n minus 1th iteration, right. So we can see at the nth iteration, the nth minus 1th gradient also has an influence. So at the nth iteration, the gradient update with the momentum is given as this equation, which is Wn plus delta W plus alpha times delta W at n minus 1th iteration. Now let's look at the velocity update term, which is delta W. It is given as g of n plus alpha times delta W n minus 1. So g of n is actually our delta Wn, right. Now let's look at the recurrence from, let's say, the first iteration to the nth iteration. So during the first iteration, delta W at the first iteration would just be G1, delta W2 would be G2 plus alpha times G1, delta W3 would be G3 plus alpha times G2 plus alpha square times G1, right? And this can keep iterating till nth iteration. So now let's look at the general form at, let's say, kth iteration. At kth iteration, delta W at kth iteration is given as summation j from 1 to k alpha k minus 1 g of j, right? Now if we follow this general recurrent form, at the nth iteration, let's look at the influence of the nth gradient, n minus 1th gradient, and so on. So the current gradient, which is at the nth iteration, the value of alpha is alpha n minus n, which is alpha to the power 0, which is 1. So the gradient, the influence of the gradient for the current iteration is 100% influence. Now let's look at n minus 1th gradient. So when j is n minus 1, this becomes alpha n of n minus 1, which is essentially only alpha. Let's say the value of alpha is 0.9, then the influence of the gradient at n minus 1th iteration is 90%. Now let's take a look at 2 steps prior. So for n minus 2th iteration, it is alpha n minus 2, which is alpha square. Let's again assume alpha value as 0.9, because alpha value would remain constant throughout the whole training procedure. Then the value or the influence is now 81%. So as we observe, the influence of the current gradient is 100%, the influence of the previous gradient is 90%, the influence of n minus 2, which is 2 times its previous, is 81%. So we can see that the influence of previous gradients keeps decreasing with the nth gradient, right? And so let's see what is the resulting behavior. The resulting behavior is the first case where eta is large. If eta is large, then we used to observe a zigzag behavior or an oscillatory behavior. However, now the alpha terms will have opposing signs and cancel each other out, hence it would smoothen the part. Second example is when eta is very small or it is low. If it is low, then we saw that the convergence is very small. However, if the gradients all point in the same direction, the sum grows quickly, allowing the model to race through the flat regions, right? Essentially, when the gradient descent algorithm is very slow, due to the momentum, it would actually gain momentum and it would race through these regions. Okay. Now lastly, let's take a look at the effects of sequential update. So we saw that how a learning algorithm is working, and this is a standard algorithm that even we observed in the last lecture. So the standard procedure is, let's again initialize the weights randomly. So let's keep it as normal, mu 0, standard deviation 7%. Now while the algorithm has not converged, let's take one particular sample from the data set, let's compute its gradient, and then let's update the learnable parameters. Since we are doing it for W1, W2, we are focusing mostly on theta, which is the learnable parameter, right? Now we can observe one interesting fact here. So let's say that our data set D is given as x1 comma d1, x2 comma d2 till xn comma dn, right? Now the way the stochastic or the online learning works is, we would essentially choose, let's say, x1 d1, we will calculate its corresponding error, and then we would have a gradient update. Then we would, let's say, take another sample, let's say take xn comma dn, calculate its error again, and then update the weights, right? Now what we observe in this particular procedure is that the updates to the weights are performed in an example by example basis. So essentially we take example 1, then we take example 2, then we take example 3. So for each example there is a gradient update, right, and it is known as stochastic method because the training examples presented are random. So we can start with x1 d1, then we can focus on, let's say, xn dn, then we can focus on x3 d3. So the training sets which are selected, training samples which are selected are actually random, which is why it's called a stochastic method. Now it's an easy to implement method, but as you can see it is computationally heavy and it takes a lot of time since we are passing each iterations, right. An alternative to this is the batch gradient algorithm. In the batch gradient algorithm also we follow the similar procedure. We initialize the weights using normal distribution. While we are training the model, we try to calculate delta E, which is the gradient of the error, and we try to update the parameter. However, let's take a look at this particular equation. So let's again define our data set as x1 comma d1, x2 comma d2, x3 comma d3, xn comma dn, right. Now in batch gradient algorithm, the updates to the synaptic weights are performed after n examples. In the sense, let's take the first 3 example. So in this particular case my n is 3. We take the first 3 set of examples, we pass it to the single layer perceptron or multi-layer perceptron, whichever model we are using. We would calculate the average of the gradient of the error through all these samples, right, and through this average we would update the weights. Now the updates are made on an epoch by epoch basis, and for after each epoch this set is randomly shuffled. So in the first I took x1, x2, x3, in the second I may shuffle it and let's say x1, x4, xn, right. So after each epoch this set is shuffled. However, we calculate the gradient based on n examples. Once we calculate this particular gradient, we update the weights. Now particular advantages of this are, although we take n example, it does give us an accurate estimate of the gradient vector. Compared to the previous online learning, it is not passing sample by sample. It is essentially taking a set, getting the average of the gradients and then updating the weights. However, one particular disadvantage of this is, and this is something we will discuss in the later lectures, is that batch learning, if I keep increasing the batch size, is very demanding in terms of storage. So when you are using a particular GPU and you are trying to deploy your model, and if you have a very high batch size, it would essentially occupy a much larger memory, right. So it is essentially dependent on n. If n is very high, then the memory would be very high, and if n is low, then we can still manage to train our model and get a good approximate of the gradient. Okay, to summarize this particular lecture, we went over a quick recap of single layer neuron. We went over the effects of activation functions, we went over the effects of the derivative of activation functions. We also saw how dou L by dou W, dou L by dou W, which is essentially leading to delta W, which is essentially leading to a update in weights, how that is influenced by the activation function. We also saw its particular scenario of weight initialization, where there are certain cases in the learning algorithm where it could follow a zigzag motion rather than a simple trajectory of reaching the optimal value theta star. We also saw the effects of learning rate. We saw what would happen when we have a very high learning rate or what would happen when we have a very low learning rate. And to address this particular scenario, we also introduced or we also explored a different term known as momentum and the effects of momentum while training. Lastly, we saw different types of learning, which is sequential and batch learning. The next lecture would essentially focus on the curve fitting example and try to relate model complexity to overfitting, underfitting. Thank you.